How are you? Good afternoon, good evening, whatever that is. Hi, my name is Yusuf Baiji. I work for Cisco. Just a little introduction and then we can start. Some of you were here already in my first session, so I think I see some new faces. So I'll just go through a very quick introduction. I work for Cisco for the last 7 years. Mainly my area of expertise is security. Transition into various job roles in Cisco. But today my main focus is on certification. So I'm not sure if you're aware, CCI security. So I'm the product manager for that. I was just telling someone it's my job to make their life miserable to pass the exam. So I'm basically writing exams for CCI security. So this is a side thing that I'd like to do. I go to different conferences, present on security. I live in Dubai, so I come a long way. I'm not a resident of US, so hello from Dubai, the deserts. Anyone been to Dubai? No one? Not a single guy? Come on.
Were you affected by the recent cable cuts?
Oh, very much. There were 3 fiber cuts somewhere in Egypt, and so we were affected, but we were not completely down. So we're going to discuss that in one of the buffs also in the panel discussion. It was a big problem. So you should come to my place. Dubai is nice. It's beautiful. Okay, so today we're going to talk about network core infrastructure best practices. And the main objective of this session is to highlight some of the security features or some of the best practices that you can implement on your core infrastructure devices. Because if you don't protect your infrastructure, your equipment, your devices, then the network will be down. So you cannot service your customers, right? So we are not talking about securing transit traffic. Transit as in traffic going from one customer to another, or we are talking about protecting your own gear, your own equipment, your own data center. Okay? So most of the features that we are going to talk about are in relation to protecting infrastructure devices, not transit traffic. Okay? So here's the agenda. We are going to discuss a little introduction on the infrastructure protection, understanding the different routers and planes and the architecture of the different planes. And then the main meat of the session is within the third section, which we are going to talk about different hardening and security techniques, the traditional methods, the advanced methods, and how to secure the CPUs and stuff like that. So that's what we are going to cover. We will also look at the best practices on securing the CPU. So for example, if you have a traditional router, in the past, there were traditional methods to protect the router CPU, for example, different protocols, Telnet, SNMP, all that stuff. So how we used to do protection. And then we will also discuss something on this one, we are going to discuss the process itself. So for example, if you're running an SNMP process or a Telnet process or some CPU process, how to protect that individual process. And we are also going to discuss another layer of protection before the process. So before even the thing hits to your RP, the route processor. Okay, so there are different mechanisms that we can put a shield before your router CPU. Okay. So this is what the network looked like in the past, how people used to manage the network in the past. So there are different devices in your core. This is the external world. And initially, core routers were individually secured, like the design, the mechanism that people used to use were individual security. So all these red boxes is security on individual devices. But today, the architecture is such that you create a ring outside the core, and you protect the whole core as a one piece, in addition to the individual router security. We are not saying you eliminate that thing that you were doing in the past, but in addition to that, you have to put up a boundary through your network, and we will look at the best practices that how we can achieve that. So first of all, a little introduction of infrastructure protection. In security, fundamentally, we can say there are three main characteristics of a network: confidentiality, integrity, and availability. The main objective of this session, the primary goal of this session, is to discuss about the availability. And as I said earlier, the objective is not to discuss the protection of transit traffic. So for example, we are not talking about cryptography or firewalls or authentication or MD5 or something like that. We are talking about keeping the network alive, keeping the network up and running and the business going on. Okay? So if you don't have a network available live, then there is no network, right? Forget about your cryptography, forget about your firewalls, you can do nothing if your network is not running. So security today is at the heart of internetworking, and all aspects of the network design merge at the security. And today we have a model of, for the internet, we have a model of from implicit trust to an internet of pervasive distrust. We don't trust anything on the internet today. And that was not how internet was built in the past. It was an implicit trust internet, but today is completely opposite. Each packet on your network has to gain the trust of your network, of the network devices. Okay? So protecting the infrastructure itself, the devices in your core network, is the most fundamental security requirement. And many times this is overlooked when you're designing a network. And I keep on repeating that many times people think very high. They will implement tons of firewalls, tons of authentication, tons of cryptography, but they will forget about the device protection itself. Okay? So a secure infrastructure forms the foundation for a continuous business operation. Some marketing slide. So it is all about the packet. And what do I mean by that? Is when you are on a network, whether it's an internet or intranet or whatever, when a packet gets on the wire, it is some device somewhere that has to do one of the following two things. Either it will deliver that packet, so it will forward it or transmit it or move it forward, or it will drop the packet. Now, the important question is, in the context of an attack, when you are under an attack or under a problem, the question is, who and where will the packet be dropped? So who's going to be responsible? The service provider, the customer, the transit provider? Who's going to be responsible to protect you against this attack? That's a big question. And there is no clear-cut answer to that. It all depends. So we have to take different measures, different techniques to protect against this type of attacks. Okay? And I know most of you are from operators, from service providers. You will always say that the principle of your business is that you are not responsible for attacks or from your customer. Like what I'm saying is, you are not responsible to scrutinize their traffic, right? All you are doing is transit. Packet comes in, send it out. You are just like a highway, right? You don't stop each and every one, open the packet and say, is this a good packet or a bad packet? True, that is very true of an operator, of a service provider, but at the same time, you have to protect your own infrastructure from these bad packets, because you are also a target of those type of attacks. So if they take your network down or your link down, obviously your customer is going to be affected. Okay? So there are two types of threats. There is internal threats, and I think in my previous session we talked a lot about internal threats, and then there are external threats. This session is primarily going to focus on external threats. My previous session, layer 2 attacks and mitigation techniques, were primarily focused on internal threats. So in these slides, the ones you are going to see now are going to be how to protect from external attacks. So one disclaimer before we move forward is that the techniques that we will discuss so far in this presentation are extremely useful, but you have to take a balanced approach. Don't put them all in one time. Don't put them without testing it. There are different parameters and different thresholds for each feature that I'm going to discuss. And they should not be just like used the way I discuss it in this PowerPoint. Okay? So you have to carefully take a measured approach. As I said, it is not uncommon to take 6 to 12 months to actually balance the threshold, the numbers, to say, okay, I want to block attacks at this particular rate, or I want to implement these 2 features to block this rate. It's not like a silver bullet that you go back and implement all the features that we discussed today. That's going to be a wrong approach. Okay? It's just a small disclaimer, because sometimes audience take, like, whatever I discuss is the final thing, and they go back and start configuring it, and then they blame on Yusuf. Yusuf said to do that. So I'm just a disclaimer. So understanding different routers and planes. So what is when you are using a network device, and particularly I'm talking about a layer 3 device in this case, the traffic that is handled by that router, that device, can be divided in different categories. So the traffic that you see on your box can be divided in different categories. Now, there are different variations of these categories. So the IETF defines those categories in 2 types: control category and forwarding category. The ITU defines it in 3 types: control, management, and end user. Cisco generalized into 3 categories. They call it control plane, management plane, and data plane. You must have heard about these terms: control plane, policing, and all that. So it comes from here. So we generalize all this from IETF and ITU. We say, okay, we'll just say control traffic, management traffic, and data traffic. Okay? So this is all the box sees the traffic from different types. So we're going to see what these different types of traffic looks like. So the first 2, the control and the management plane traffic, are always traffic that is to the device, to the box itself. Okay? However, the data plane traffic is always through the box. So that is called the transit traffic. Okay? Make sense? And I have a slide to show you more explicitly what that means. Control and management are to the box. Data is through the box. But this slide says that there are situations when some of the data traffic can also be to the box. Okay? So the situations like, for example, ICMP unreachable. So for example, there came a packet which originally wanted to go through the box, but because there was no route in the routing table, the router had to generate an ICMP unreachable. So that way it became a control plane traffic instead of a data plane traffic. Okay? So there are situations where data plane traffic can also go into the control plane area, into that segment. So let us look at the architecture of a basic architecture of a device, a hardware device such as a router. Okay, what is it made up of? And these are some high-end routers, okay, in a service provider environment. So let's say this is one line card of a router. The packet comes into the switch fabric. There are different ASICs for different functions. So before the ASIC processes and forwards it to the packet, there are some functions that it can go to the supporting ASIC, and then it can go to the route processor, the CPU, come back and then forward it to the switch fabric or the other modules in the chassis. Okay? So this is the basic operation like this. Okay? So in the same context, what is the data plane traffic look like? It goes through the box. It doesn't go to the processor or the ASIC. It goes through the box. That is all packets forwarded through the device. That is called the data plane, the data traffic. Data traffic is very simple to understand. But let's see the control plane traffic. Control plane are all those traffic which actually go to the RP, such as your routing protocols, BGP, OSPF, or any other thing that glues the network together. For example, ARP, DHCP or something, anything that is control plane. Okay? And then we have the management plane, such as device management, for example, telnet traffic, SNMP, FTP, all that also goes to the CPU. So you understand that there are different categories, and we in Cisco we divide them in 3 different categories: control traffic, management traffic, and all the remaining is the data traffic. Okay? So there are some traffics, as we said, in the data plane that can end up going to the ASIC. For example, I said the ICMP unreachable example. So originally it was supposed to go through, but then there were situations where it had to be processed by the CPU and go to the RP and then go to the switch fabric. And I told you an example of ICMP unreachable. Okay? So what are the different, now in relation, in context to this, why did I tell you all this? We want to establish what are the different places or issues that can happen with this design. So when there are 3 types of traffic, data plane, control plane, and management plane, either it goes through the ASIC or it goes directly. There are different queues, different memory, different buffers in the router that are holding all this traffic. So you can saturate those queues. You can saturate the PUN queue, you can saturate the supporting ASIC CPU, you can saturate the CPU itself, you can saturate the input buffers. There are different places in the device that you can actually target and attack. It's not just like one box that you can attack the box. The attacks are very specific. Some attacks are focused on saturating the CPU. Some attacks are focused on saturating the ASIC CPU. Some attacks are focused only on PUN queues. So you have to understand the different areas in the architecture of the box, because there are different functions, different ways to mitigate them. Okay? So now we talk about the different protection mechanisms that are available to protect against these type of problems. Okay? Now, this slide that I'm going to talk about, the traditional methods, are very common methods, and I have 2 slides which I've tried to summarize all the traditional methods. I'm going to just shed some light on it, but the traditional methods are so extensive that we can actually take a whole session of 2 hours to discuss just on the traditional methods. So the main objective of this presentation is the second piece and the third piece. So I'm not going to spend a lot of time on the traditional methods, but I've tried to summarize them. Most organizations have their own best practices. Cisco has also recommended a lot of best practices in traditional methods, okay, which you will see in my next 2 slides. However, apart from Cisco, you can also go to these other organizations like IETF, SANS, who have listed some of the best practices of the traditional hardening devices or hardening your routers in your infrastructure. So we will review some of the common traditional best practices that Cisco recommends. So here's the first slide. For example, disable any unused protocols. You do these commands. Configure access lists on all your management VTY lines. Configure access lists on all your SNMPs. Disable SNMP read-write. Prevent dead TCP sessions from utilizing VTY lines. For example, when you're managing a box, when you telnet to the box, you use up one VTY line, right? There are like, let's say 5 VTY lines on the box. So if I do 5 telnet sessions, all of them are used. But when you disconnect one of the session, it doesn't clear up the line. So you have to configure this additional command called service TCP keep alive. What this does is sends hello packets to TCP session. Are you there? Like, are you still alive? So if there are 3 of them, it sends, and it misses one of them, it says the session is no longer, and it clears the TCP table. Okay? So these are most of you don't do this, but you should be doing it. QoS enforcement, use secret passwords, run AAA, disable extra interface features, and I think in previous sessions we discussed about the no IP proxy ARP and no IP redirects. So I'm not going into every detail of them, but just I've tried to summarize that these are, I mean, I can safely say 70 to 80% of things that are in these two slides, you must be doing it. If you're not doing it, please consider them doing it, okay? Because these are like kind of like 101, hardening device 101, you know? Source address validation, so IP unicast verify, URPF. I'm sure you know what URPF is. Everyone aware of URPF, unicast reverse path forwarding? It's a very common feature on a router. You should be using that. Disable source routing. Now, again, this is debatable. Source routing is a function that you can craft a packet and poison or override the router's ability to set the next hop. So according to the routing table, let's say you're sending a packet to destination Y, XYZ. Router says XYZ goes from this interface, but you are saying source routing, no, send it from this interface. So you're overwriting the decision of the routing table by sending a source route packet. According to the IP RFC, this is allowed in the RFC. So Cisco IOS had to allow it because we have to abide by the RFC. But if you know that you are not using this feature, you better disable it. Okay? Most people are not aware that this is enabled on the router and it can be dangerous. You should be using prefix list if you are a BGP peer, especially if you are doing eBGP, then you should be using prefix list. BGP dampening, maximum prefix, MD5 on BGP, so all the BGP features. If you have a special hardware like high-end router devices, there are some dedicated hardware-dependent features that you should be using. SPD, selective packet discard, very important feature. Most of you may not be using it, but please consider them. So as I said, these two slides, 70 to 80%, you should be doing that. Okay? These are called traditional methods, meaning like they are 101. It's no-brainer, like you must be doing that. As a matter of fact, I'm sure most of your organization are already doing it, but just for the sake of completeness, I put up a slide saying, okay, you should be doing this. But the essence of this presentation comes in the second piece, which is how there are some new features which are explicitly targeted to infrastructure protection. Okay? So let's talk about those. So first of all, as I said earlier, in the old days, we used to enforce policy at the process level. So for example, VTY, Telnet. We used to enforce access lists on Telnet. That's called process level security. Or SNMP. We used to put access lists or read-write community or all the community strings. That was also a process level security on the process. But today there is a requirement to create another layer of security before it hits the process. Okay? So we call central policy enforcement prior to the process, which provides granular protection. It is mostly available on high-end platforms, but mostly in terms of Cisco, it's also available on mid-end small range devices also. And I'll explain that in a sec.
You're talking about 2800s?
Yes, some of them are still available in 2800s, but things like this, receive accesses are not. They are only available on high-end routers. Okay? So there are some which are available on only high-end devices, like the RACL that I'm going to talk about, but there are some like COP, control plane policing, they are available on small, medium, high-end range, all of them. So let's discuss the first mechanism that is very important, receive ACLs, RACLs. How many of you here use RACLs? 1, 2, 3, that's good. It's a good start, but you should be considering if you have high-end boxes. So receive ACL were introduced on GSRs, 12,000, 7,500, 10,000 series, and they are nothing but they are an access list on high-end box. You know the traditional access list, the extended access list. They are the same thing, but they have a very different function. And then I'll explain that in a second. So they are just like regular access list, standard, extended. You can use show access list command to check the hit counts and all that stuff. But what does it do? What does it do especially on high-end boxes that are absent in the low-end boxes. Receive ACLs filter traffic destined to the route processor via the receive adjacencies. Something very scientific. In a nutshell, receive ACL filters traffic which is targeted to the route processor. So control plane and management plane traffic. We are not talking about data plane traffic. Your regular access list will only monitor data plane traffic. Receive ACL will monitor control plane and management traffic. Okay, and I have a diagram. So let me show you a diagram and I'll come back to these slides. Actually here, see, RACLs do not affect the data plane. So let's see this diagram. This is a 12,000 router. This is your switch fabric. This is one line card, another line card. Receive ACL sits before the switch fabric, before the line card. So there are two types of packets, right? There is a packet which goes to the router, that is called control and management plane, and the other type of through the router, which is called the transit traffic. Again, receive ACL is not meant for transit traffic. Receive ACL is meant only for this red line, for the packets to the router. So let's say a packet comes in from an interface. Which type of traffic is this? Through the route, data plane. So it doesn't touch the receive ACL. See, it goes to the switch fabric, does all the stuff and goes out of wherever it had to go. However, another type of traffic comes in which is to the router. So it is processed by the receive ACL before it hits the route processor. So receive ACLs are meant for traffic that are destined to the RP, control plane and management plane. Similarly, if you see here also it goes before it hits the RACL, but again another traffic, oops, all the yellow lines are non-control plane and data management plane. They are all transit traffic. Transit traffic are not affected by RACLs. So now we understand the objective of RACLs. They are different from your traditional ACLs. So going back to my previous slide, receive ACLs explicitly permit or deny traffic destined to the RP, does not affect data plane. Traffic is filtering ingress on the line card prior to the RP, and you just saw the diagram. Before you hit the route processor, it sits before at the front of the line card. So any packet coming in, it has to go RP, it will be inspected by RACL. Okay? Very, very effective and very useful. So how does it do that? It establishes using the Ceph adjacencies. So for example, when you do show IP Ceph on your high-end box, anything which has a next hop of receive, that traffic will be inspected by RACL. So just as a FYI, how will you know which type of traffic will be inspected by RACL? When anything over here next hop is receive. Because whenever it's received, that means that traffic is sent to the RP for processing. Okay? So for example, here you can see multicast traffic, some other traffic, some network traffic, I don't know. So we saw this diagram. Any questions what RACL does or what is the function of RACL? Okay. No. The question is it available on 6500 platform? The answer is no. Only on 10,000, 7200, 7500. 76 I'm not sure, but I don't think so. I'll have to check. You can easily check on the feature navigator. Have you used FN, feature navigator on cisco.com? Just as a FYI, out of topic, whenever you want to check any function or a feature in a Cisco device, you go to www.cisco.com/go/FN, feature navigator. When you go to FN, there is a table which says you want to search by product, search by feature, search by revision number, iOS. When you search by feature, you get all the list of features on the left column. So maybe there is RACL, receive ACL. You click that, put it in the right box, search, and it will list you all the hardware and software that this feature is supported on. Very effective tool. Okay? Okay, coming back to receive ACLs and fragments. Receive ACL can also inspect fragments fragment in packets. And not only it can inspect fragment, but it can inspect fragment on a per protocol basis. So UDP fragments, TCP fragments, IP fragments, ICMP fragments. Okay? So it is very granular in that manner. So how do you create a receive ACL? Like if you're a first timer, you just started on a box. So what access list should I write in the receive ACL? So here is a process. First of all, the process of creating receive ACL is iterative. It's continuous. It's not like one time you just write it and forget it about next 12 months. It's a continuous process. You develop a list of required protocols. When we say required protocols, meaning that box that you're configuring ACL on, what protocol is it running? Is it running OSPF? Is it running EIGRP? Is it running BGP? Is it running SNMP? What is it running? So you have to establish all the protocols. Then you develop an address requirements. So if you're running BGP, what is the source address? What is the destination address? Obviously destination has to be this box. But on this box, what is the address? Is it the serial 0? Is it the Ethernet? Is it the loopback? What address?
Why is a receive ACL superior to a hardware ACL? I mean, it's happening later in the packet path. So wouldn't it be better to apply the same list of requirements and rules in a hardware ACL before?
But that again depends on the hardware limitation. It's not available on all the platforms.
But the platforms you mentioned in the receive ACL do kind of.
Yeah, but the question is, why don't we use the hardware ACLs? Because there are different line cards and different requirements for the hardware ACLs, very, very specific. Yeah, something like that. But receive ACL is generic, like an access list, global. So it is any packet coming in, it will inspect, regardless of what modules populated in your device. So determine the interface, whether you're using loopback, you're using physical addresses. And as we said, that deployment is iterative. You start with a very open access list, like permit any OSPF or any EQ BGP, and then you gradually tune to specific source and specific destinations. Okay. Now one way to do that in the step 1 is what we call classification ACL. Everyone know what classification ACL is? You want me to explain? Classification ACL is nothing but a bunch of permit statements, your regular ACL. So you say permit TCP any, permit UDP any, permit IP any. So classification is just your monitoring traffic going through. You put a log keyword on each line, and as the traffic comes through, you monitor show log. And you see what traffic is going on through the box or to the box. And as you learn the traffic patterns through the classification, you put a note, oh, okay, BGP is coming from this source to this destination. OSPF is coming from here to here. You learn your traffic patterns. That's called classification ACL. So you use classification ACL to determine the protocols, the ports, the source addresses, the destination addresses that are in use. Now, why are we doing this? Because some Mr. Nice Guy came and said, here, Yusuf said use RACL, configure it. Now you have no network diagram, you have no topology addressing, you have nothing, you're just sitting on a box. Where do you start? This is where you start. You start with a classification ACL. It's not that you tell your boss, how do I know? Where is it coming from? Where is it going to? You don't say all these things. You can learn that traffic because it's going through your box, right? So again, it will take some time to polish your ACL, but you can create a whole list of things that are going through your box and to the box. Okay? So in the first step, you identify different protocols, port numbers, source address, destination address, and in the second step, you actually apply the receive ACL learned from your classification ACL. Okay? On the third step, you restrict, you are fine tuning again. On the first step, maybe you did any source, any destination, any EQ, BGP. So you are saying allow anything BGP. But in the third step, maybe you are saying, okay, instead of any, I want to restrict the whole /27. So I borrowed this from the service provider, this /27, so I'm taking this whole subnet. Okay? So you kind of trying to polish your ACL. In the fourth step, you are narrowing the ACL to the specific source addresses. So for example, let's say AAA. So you know explicitly what is the source IP address of the AAA server that is communicating radius to your box, right? You know that information. So you can hard code that source address of the protocol that is communicating to your box. Again, not through your box. Make sure. And then you can also destination address. So for example, if that radius server is talking to your box, which IP address is it talking to? The physical address, the logical address, the real, the serial 01 or serial 00, which address? So you have to hard code the explicit source, explicit destination equals the protocol radius. So that is the final step. And then you do the repetitive process and you fine tune your ACL until you get a very fine 10, 20 lines of ACL saying this is the exact traffic that is going to my RP. Make sense?
Is SSH traffic to the box? Is that
To the box. SSH is to the box.
yeah. Anything that goes to the box?
Anything to the box. Control plane traffic and management traffic. Telnet, SSH, FTP, SNMP, NTP, all that is management.
So left out stuff like show IP, OSPF, neighbor, show IP, BGP.
You can use any mechanism. You can use all those show commands also to establish what is the source and the destination, or you can use the traditional classification ACL to establish what are the exclusive source and destination. The bottom line is, at the end of the fourth or fifth step, you should have a fine-tuned ACL which is allowing only single to single, not like any to any or /27 to /24, or you have to be very specific. That's good. Otherwise, if you open it up more, /24 or /27, you are opening up more wider. So you should be /32 to /32. Make sense?
All those other commands are specific. Show, IP, PIM, neighbor, they're all specific.
Specific, but some are not, which is why you need the classification ACL, right? So for some protocols, you have very specific commands to establish the source and the destination, right? But for some traffic, there's not, like telnet traffic. Now you don't know where the telnet is coming from. So you have to, through the passage of time, establish who is managing this box, from which subnet, from which VLAN do your users telnet to this box or SSH to this box, and then you explicitly allow them. So here is a simple example. I don't want to go through this. These slides will be available to you on the web, on the NANOG website. So you can, on your own sweet time, you can review it. So fragments, OSPF, BGP. So let's take one example, BGP. So you see, you permit TCP host, explicitly that source host, BGP peer, to your router loopback equals BGP. You didn't say any, or /24 to /27, or like explicit, like one line, the BGP source address, the destination of this router, whether it's loopback 0 or serial 0 or Ethernet 0 or whatever it is, you put a single host address here. Okay? Same for EIGRP, same for SSH, same for SNMP, trace route. Trace routes is a good example. When you do trace route from the box, I'm not talking about transit trace routes, that a client did a trace route to a web server on the internet. No, I'm talking about, again, we are talking about RACLs, and we are talking about traffic to the box, control plane traffic, management plane traffic. So when you initiate a trace route from the box, trace route goes out, the return packet are called type 11 code 3, ICMP type 11 code 3, and type 3 code 0. These are the two packets that you need to permit in your ACL in order for the return packet going back to the RP. If you don't permit, your trace routes will fail. From the box it will fail, not through the box. Okay? So make sure. Now one important thing, the last line. After you fine-tune all these ACL, what should be the last line of our ACL? Deny IP any. Why? Because other than the ones you permitted up before, you don't want any other traffic going to your RP, to your CPU.
Isn't there an implicit deny at the end of
Yeah, there is, but we are just emphasizing here that that is what the deny should be. Because when I'm going to talk about my next feature in IACL, infrastructure ACL, in my next slides, in that one the implicit we say permit any. So I'm trying to make a point here that although there is an implicit deny at the end, but you should explicitly deny it, maybe put a log keyword so you want to see if there's any bad traffic going to your RP. Okay? So in summary, RACL sits here before the process. So that is the processor. RACL will stop anything going to the process, whether it's a OSPF or BGP or Telnet or whatever. Okay, it protects the route processor. Now, if you have a platform that supports RACL, start planning to deploy it. But many ISPs uses RACL in conjunction with a new feature called COP. COP means control plane policing. Some even call it CPP. So control plane policing is very, very important, very scalable. Actually, it's a superset of RACL. It's an advanced version of RACL. Okay, so that's what we are going to discuss next. Any question on RACL? So let's discuss about control plane policing. So as we said earlier, RACLs are great, but they are limited in terms of platform. I mean, if you're using 6500 or 3800 series or some lower end, you cannot use RACL. So how do we protect the RP on those boxes? The answer is you use control plane policing. Another not disadvantage, but another thing that you cannot do in RACL is do rate limiting. So for example, RACL is either permit or deny. You can't rate limit, say, up till 8,000 bits per second, allow it, and after that drop it. You can't do rate limiting. You can't do thresholds. Either you permit or you drop. But with control plane policing, you can do rate limiting. So think ping. You want to allow ping, but you don't want to allow a DOS of ping. Right? So you want to rate limit the ping. So control plane in that manner is more flexible, more granular, and it has more options, more than permit deny. It can do rate limiting. Now, how does COP work? COP uses the underlying architecture of COP. It uses the MQC feature, which is another feature in iOS, modular QoS CLI. And originally, a lot of QoS features on the box have now turned to be security features. It's just been like that. Traditionally, the functions or the features which we used to use for QoS mechanisms, now we have started to use it for the security functions. The advantage of using the MQC for the COP is the consistency of the iOS in all the boxes. So whether you're using 2800 series or 3800 series or 6500 or 8000 or 10,000, it's a consistent feature throughout the box, throughout different series. Okay? In addition to the MQC, there is a dedicated logical interface, a virtual interface on the box, which we call control plane interface. It's just like, how you have loopback interface. Similarly, we have COP interface. So all you do is you create MQC policies and you apply it on which interface? You don't apply it on the serial. You don't apply it on Ethernet. You apply it on the COP interface. And I'll show you an example so it will be much more clear. So from a diagram perspective, look, this is how it looks like. Remember in RACL, I showed you how the packet goes to RP. Similarly, let's say these are incoming packets, outgoing packets, goes to a buffer, looks up the CEF, fib, goes to the RP. Now before it goes to the RP, the control plane sits here. So it polices everything over here. Then once it's cleared, it goes to whatever function it was supposed to go. So these are the functions, the different telnet, SNMP, protocols, BGP, OSPF, all the control plane and the management traffic. And then it processes that function, goes out, and goes out of the box. So COP sits here. Now, most effective implementation of COP is inbound. Obviously, you do inbound. But, however, there is also an outbound COP that you can apply. And when can you use COP for that? It's mainly for prevention mechanisms. But over here, it is more like a proactive. You don't allow traffic going to the protocol in the first place. So that is the best practice to apply inbound. So when was COP introduced? Yes? Say again?
Does it sit in the route processor?
The question is COP, does it sit in the route processor? No, it actually sits before the RP. So before the traffic goes to the RP to be processed for all the control plane. No, it is not dependent on the line card. Yes, if it is a hardware which has a line card, yes, but since COP is available, things like 1800 series router, there is no line card in 1800. So you can imagine the architecture is different than receive ACLs. It's in the ASICs, absolutely. So it was introduced, the COP feature was very, very powerful, and it was originally introduced just like the receive ACL on high-end devices, on the 12,000 and 6500. But then, according the demand increased and customers wanted more of COP, so Cisco ported the COP feature on all the boxes. You buy any small end, high end, medium range, COP is available on almost all the series, all the new series routers. Not the old 2500s or 2600s, but all the ISRs, all the ASRs, all of them.
So there was a cert one time saying that, but then I had the service tag was, launched against the COP, function. I mean, has that been fixed? You should use it actually for the cert saying.
Yes, there are always different vulnerabilities in different functions, and that has been fixed in newer iOSs. But I'm not too sure which ones, so maybe I'll have to research and get back to you.
Where it says 6500 there, is that every processor ever made, or just the Supervisor 720?
No, just the SUPs. So it's the
Supervisor 2?
yeah, SUP 2 also, because the COP feature is only going to monitor traffic going to the RP, right? So any supervisor engine. I think it started on, I think I wrote it somewhere here. SUP, I have a very specific model number. It started, I'll tell you exactly. SUP 2 was the minimum, I think, so not on SUP 1s. But see now, I mean, those are all legacy anyway, so it doesn't matter. If you're using that, you start thinking of upgrading. So, okay, so one option, you can see COP as an advanced RACL function, just like an RACL, but a little more than RACL, right? And the important thing about COP is the platform, how should I say, the availability of wide range of platforms. Yeah, okay, now going to the steps, how do you apply COP? It's a little similar approach to RACLs, but if you have configured MQC, the modular QoS CLI, yes?
On the previous slide, you had an example of actually creating a COP interface, and it said, slot number.
Yep.
What do you use for that?
For the high-end devices, when you have a modular?
500, what do you select? Are you selecting a specific module interface?
No, not on 6500. This is for the GSRs, not 6500s. So on even 6500, you have control plane enter, and you just apply it globally. Okay, this is for GSRs. Because originally this COP was introduced on GSRs, on high-end series. That's why they still have this distributed slot numbers.
So that's for slot numbers if you have dual RPs.
Not really. This is was on a per RP on a per slot. So each module had its own RPs. So you had COP per RP per slot, not globally. Okay, as I was saying, when you want to configure COP, you have to be very familiar with the MQC configuration style. So if you've configured modular QoS CLI, configuring COP is no difficult. Okay. So first thing you do in configuring COP is you define the access list, you classify what you want to do COP for. Do you want to do COP for your OSPF traffic, for your BGP traffic, for your telnet traffic? Then you define what we call a class map. Class map, you refer the ACL in the class map that you call different, so you can do different segments. So you can say all the OSPF, all the telnet traffic, all the SNMP traffic, you can distribute them in different buckets. And then all those buckets you can distribute in different class maps. Why? Because you want to take different actions on different buckets. So for example, you are saying for OSPF, rate limit this much, for BGP, rate limit this much, for telnet, you want to rate limit this much. So you have different actions, different policies for different buckets. So you have a very granular way of classifying your traffic. Okay. Finally, when you have class maps, then you define the buckets and then you apply the rate limiting or deny or permit. So for example, for some buckets you simply want to drop traffic. For some buckets you want to permit but at a certain threshold. So you have variations. Okay? And finally you apply the COP on the interface. Which interface? On the COP interface, not on the serial, not on the Ethernet, not on the loopback, but actually there is a COP interface dedicated on the box. So I have a very good example here to walk you through all these 4 steps. So let's see the first step, defining ACLs. Now this is just for an example. It's not necessary that you should follow the same example. Okay. So let's see. I have created different buckets for different type of traffics. So first of all, my first bucket is pre-undesirable traffic that is deemed bad or malicious and should be denied to the RP. I don't want this traffic going to the RP. So that's one bucket. Second bucket is critical, every traffic that is crucial to the operation of the network. Third bucket is important. Important meaning it's not like extremely crucial, but they are important. So all traffic that is necessary for day-to-day operations. Then another normal traffic expected but not essential for operations. So you need the traffic, but they are no high priority. Okay? Then post undesirable, which is similar to pre-undesirable, but it is depending that before the inspection and after the inspection. And then finally catch all other IP traffic that is going to your RP. Okay? So these are the different buckets. So I have listed here all the buckets, the pre, critical, important, normal, post, catch all this. And we are associating different access lists for each bucket to capture the different traffics. So let's say the first bucket, ACL 120. What are we matching? Traffic that should never go to the RP. What type of traffic? Any fragments, TCP, UDP, ICMP, and any traffic which is UDP, any EQ 1434. Which is this traffic? Slammer worm. So we don't want SQL slammer worm going to the RP. So we are classifying all the bad traffic in one bucket. Now this list can go on. It depends what you don't want in your network. But in my example, these are some of the traffic that I don't want to go to the RP. Then we design the critical bucket, all the routing protocols, so all your BGP, all your different multicasts, all the OSPF, all the critical traffic that is important that you want to go to the RP and should be given a priority.
How do you deal with ISIS?
Yeah, you can also,
It's not a big product. Right.
but you can classify it.
You can classify it now?
Yeah,
It used to be that you...
yeah, I'm pretty sure you can classify it now. But I'll have to look it up. But see, from a logical perspective, this is just to give you an example that you create different buckets for different type of things, right? If you cannot classify your ISIS traffic, there must be a way to characterize that No, there has to be one. ISIS is a very core protocol. There has to be some way to classify it. Yep, you would think so. Important traffic are all those which are required in your day-to-day, but they are not critical. They are not business critical. They are important. So things like, SSH, management protocol, telnet protocol, TFTP, SNMP, network time protocol. So these are not business critical, but they are important. They need to go to the RP. Then the normal traffic, all the trace route traffic, ICMP, echo reply, all that stuff. Then all the traffic that should never go to the RP after all these inspections. So for example, you have allowed telnet, let me go back to this ACL. So let's say you have allowed telnet from this subnet 10.2.1.0 to this host 10.1.1.0 telnet. But you are saying that is important. But on this access list, you are saying anything other than that. All other telnets to this IP address should not go to the RP. So it's like post-screening, not pre-screening. That's why we have these two screenings, pre and post. Okay? Because it will go sequential, your access list. Then you catch all other traffic, IP, NE, and default, there is no access list required for the default. So once you have established all the categories of different traffic going to your route processor, then what do? You map these access lists to the class maps. So you have now, if we have 6 access lists, then we need 6 class maps. So what we will do, we will create 6 different class maps. Just for the naming convention, you can use any naming convention, but we named it to the same category, and we are matching each access list to its corresponding category. Okay? And the third step will be to put the action. Action meaning, now what if this traffic is matched? What do you want me to do? Do you want me to permit it? Do you want me to deny it? Or do you want me to rate limit? So that action is the third step which you put in this policy map. So if you go back, you did the class map, and then you do policing under the class map. Now this style of configuration is typical the MQC style, modular QoS CLI. For those of you who have used MQC, they know what I'm talking about. So you classify traffic, then you classify the action for that traffic. Okay? And this whole thing is under one single policy map, which we can call anything ABC. And this policy will be applied to the interface, the COP interface. Okay? So in this case, where is it? We apply the service policy inbound. Remember this word COP comes from here, the policy map COP. So we had the policy map, we had different classes, we had the different actions in each COP, in each class map, and we apply that policy to the interface control plane. Okay? So if you have a distributed hardware, you have the slot number, but in the most hardware, it is a centralized. You just say control plane and hit enter. You will see that CP thing here. You apply your service policy input COP. So as I said, the direction is both input and output, as I showed you in that diagram. But the best practice is to apply inbound on the RP.
What about the actual values? Because, GSR is good.
So coming back to the values, this policing, they are variable. That depends on the box. That depends on your policy. Like for example, in this one, the pre-undesirable traffic, if you go back, what did we classify in this? So in pre-undesirable, we classified all the fragments, all the SQL slammer. We completely don't want this traffic to go to the RP. So what was our action in the policy map? In the policy map, we mentioned that whenever you match this type of traffic at this speed, what should be the action? Drop. Irregardless. Confirm action meaning it is adhering to this bit rate or exceeding the bit rate. In both situations, we are saying drop. But at the same time, on the other critical one, we are saying confirm action, transmit. Exceed also, we are saying irregardless. If it is exceeding the threshold that I have defined, you still prioritize it and transmit it.
So if the conform and the exceed both have the same action, then the values that you put in for the rate don't make any difference.
Don't make any difference because you are still saying that at which point do you catch the traffic. There has to be some threshold that it should trigger, right? So it should trigger at this point. That is the lowest minimum point.
Or that if it conforms or it exceeds, regardless of, you're still going to do
Yeah, but if you don't, then it is going to be subject to the default category.
The first two categories, your free undesirable and your critical, those numbers for the rates are just a placeholder.
Yeah, but these are placeholder, but this bit rate is smaller, and over here it's higher.
But does it matter? Because your conform or exceed both drop and your conform or exceed both transmit. So it doesn't matter what number you put in there.
No, it still matters because you are allocating a certain bandwidth for that particular bucket, right? And you are saying this is in relation to this bucket.
Okay.
So if you don't do that, then that traffic will fall into the default bandwidth,
Okay.
the default category, which is default class. So you have to put some threshold for the memory, the bandwidth. That depends on these numbers are artificial. These numbers are artificial. That very much depend on you're using 2800, 3800, 6500, GSR. And again, how much do you want to prioritize? Do you want to go on upper limit? Do you want to stay middle, or do you want to go lower limit? These numbers are subject to your policy, to your security policy.
How come there is no recommended range for each one of the boxes?
Because there is no silver bullet for all the different type of networks.
Excuse, but, in actuality, these processes can only take so much.
You speak to any security consultant, they will always give you some recommendation, but they will not hold it to it. Like, you know what I'm saying? Like, they won't say, okay, these are the actual numbers that somebody quoted me. They will never be on Cisco.com or SANS, or they will never print numbers, recommended numbers. They will recommend a procedure, but not the numbers. You have to observe the network. They will never.
They need it for the smart grids to see what.
Yeah, I mean, you have to monitor the network. No vendor or no organization or no one will give you the numbers that what are the best practice, that how much RP traffic should you pump to your RP. You know, you won't get those numbers. Numbers, I mean, you can say 1/3 or 1/10 or 1/5 like that, but not actual numbers.
Well, you know, I want to go back to his point about what do those numbers mean when the conform and exceed actions are the same, because I don't see how that has anything to do with the default class at the bottom. Traffic either does or doesn't match the default class depending on what class.
No, but if you consider like the bandwidth, the whole pipe, they want to slice it for different categories, right? So if you, for example, if you don't fall into this category, that traffic will use the bandwidth of the other category.
But if the actions are the same, if you're going to transmit the traffic regardless of whether it conforms or not, or if you're going to drop the traffic regardless of whether it conforms or not, then what do the numbers, what difference does it make if I put different numbers in there?
Let me think of how to answer this.
There's one very good application, and that's when you actually start to define the numbers, and you don't really know how much ARP is on my network, how much SNMP is on. So you put conform, you put transmit in both of them, and you'll do, when you do show policy map, yada yada, you will see how much traffic exceeds, how much traffic violates,
Here.
how much, so you can
Okay,
choose.
so for a classification, yes, I can see that, okay.
Yeah, I mean, again, multi-purpose, right? You have that objective for multi-purpose. So here what the gentleman is saying, this is the command that you use to track each bucket. So let's say how many packets at which baud rate was confirmed and how many exceeded. So you can actually know, okay, there were 16 packets that confirmed or there was 0 packets that exceeded. So then you can start tuning that number again and then change the exceed from transmit to drop maybe. Another thing that that is not mentioned on this is, in other than the confirm action and transmit action from the value from here, drop and transmit, there is another action which is called precedence. So you set the precedence value, set IP precedence, so you can tag the traffic. Why are you tagging? So that when it goes through the other path, the action can be taken on the other path. So you tagged it as a priority precedence or critical precedence or some low precedence.
That would be on your outbound.
Yeah, wherever. This is just, I'm saying that there are various values that you can put. You can drop, you can transmit, you can set precedence. There are different options that you can do. So again, as I was saying, this slide, maybe it is a source of confusion. Why? Because we just made this up. There is no real meaning to these numbers or these actions. That is why, as the gentleman asked, that what is the best practice? Don't take this as best practice. This is just, I'm trying to show you the syntax style, that first there is policy map, then there is class map, and then there is policing. You can choose not to police. You can simply say here permit or deny or do something else instead of policing. There are multiple options under a class map that you can perform.
Yeah, why wouldn't you just deny all the ones that are undesirable?
Yeah, you can simply do another action. There is an action over here under the class map. Instead of police, there is an action called drop. Just simply drop, drop. So you just say anything that matches this class, you just drop it. Forget about policing. So as I said, this is just an example. Don't strictly follow it, but it's just trying to explain you the format of the syntax of the COP, how to configure COP.
Some of the processors, like 7600, the line cards actually do ICMP rate limit just like this.
Yes. And you can use,
Included twice.
Yeah.
Because it's already being done by,
yeah, but that ICMP rate limit is not for the RP traffic. Maybe it could be for transit traffic also. This is explicitly for traffic going to the RP, right? That command that you are saying is also for the data plane traffic. This is for RP only. This is not going to apply for data plane traffic. Make sense? Just like receive ACL. But, oh sorry, I take that back. Actually, control plane policing can do data plane if you configure it that way. But the primary objective is to use COP for data plane, for the control plane and the management plane traffic. However, you can still inspect data plane traffic with COP, but that is not the objective. On the flip side, receive ACL was strictly control plane and management plane. You could not inspect the data plane traffic with the RACLs. Okay?
If you're applying it to the COP interface, how would COP inspect data plane traffic?
For data plane traffic that goes to RP, that punts to the RP, not the regular data plane. There is no point in doing rate limit control for the data plane traffic. Only for the one which go to punt to the RP. Okay, so you can monitor using the show command as we said earlier. So again, similar to RACL, COP sits before the CP, the RP, before the processor. So if you are using any process, BGP process or SNMP process or Telnet process, it sits before that. Okay, so it's protecting the process. It's more centralized, more distributed, blah, 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 blah. Okay, so now we discussed about the protecting CPU. Now we talk generally about protecting the hardware itself in terms of ingress traffic. So for example, on a general note, in context of DOS attacks, if the packet makes it to the router, like actually arrives on the router, then it is already too late because the router has to process it, right? So maybe COP and RACL are good, they will help you, but it may be too late because you are already subject to that packet. You already have to inspect and protect that packet. So you really need to drop unwanted packets at the door, at the ingress, before it comes in. Because RACL and COP are packets when it already comes. So for example, if this is the router, it comes inside the door, it goes to your input buffer, it goes to FAB, it goes to CEF, and then RACL and COP kicks in. But the point is we should stop somebody at the door and just kill it there before it enters the router. Okay? So for that, there are three important mechanisms. One is called IACL, infrastructure ACL. There is other feature called core hiding in the MPLS network, and then there is MPLS VPN. My area of expertise is not in MPLS, so I am not discussing more in depth about the MPLS VPN and core hiding, the VRFs and all that stuff. But as an FYI, there is these two features also, MPLS VPN and core hiding, which is creating VRS, virtual route forwarding tables. That can also be used to protect against this type of issues. But we are only going to cover one of them, so it will just give you an idea what the other two are. So let's talk about infrastructure ACL. We also call it IACLs. IACLs again is similar to the other traditional access list, but there is a logical difference. There is no syntax difference. Syntactically, from a syntax perspective, it's the same. Just like your extended ACL or standard ACL on the box. But the objective of using this is different. The reason you are using IACL is to protect traffic coming to the box, not through the box. And to the box meaning if you have, for example, BGP. So let's say you know source eBGP so and so, destination BGP this box, you should write an ACL that permits that BGP and denies all other BGP, right? So you stop every BGP traffic at the door. You're saying I don't want to process BGP packets if the source and destination don't match this. Why allow it all the way in, let it go to the RP all the way to the BGP processor and process that and then kill it, right? You will eventually end up killing it, but you are saying kill it earlier at the door. Make sense? So IACL is nothing but a list of permit and deny statements for traffic destined to the box. Similar to RACL. Similar to RACL. But this is a generic ACL on the interface level. RACL was different on high-end boxes. IACL is using the traditional syntax of the access list, applying on your serial 0, Ethernet, or FIDI, or whatever interfaces. You apply inbound on all the interfaces. So what is the best practice to configure IACLs? You permit only the required protocols, OSPF, BGP, RAE, PIGRP, OSPF, multicast, telnet, all the explicitly to the ./32 of that box. And you deny all others to the box. To the box. Okay? So for example, hypothetically, my router has an IP address of 10.111. So I say permit BGP from source XYZ to 10.111 EQBGP. So first line is permit. The second line should be deny any to 10.111 EQBGP. So you're saying from anywhere else to this 10.111 deny BGP. First line is explicit permit, second line is implicit deny. And then the third line will be permit again for another protocol, OSPF or multicast or something. So I'm dealing per protocol, per host basis to the box. Again, I keep on emphasizing to the box. And then at the end of this permit, deny, at the end you will have what? Permit IP, any. Why permit IP? Because we want to permit transit traffic. We did all the permit deny to the box. Now we should permit IP any for all the go-through traffic. If you don't do that, because you are tying this access list on the interface, which interface? Your serial facing to your ISP. Then obviously all traffic is coming in and you have an implicit deny.
When you say to the box, in a situation where you've got multiple, where if you're multi-home, you would want that to all of your core, not just
Whatever core, if you have a single address or a CIDR or a /28,
within your network.
absolutely. And you can fine tune to the interface level. So for example, if you have multiple ingress, you know that from this ingress only this core is going to come in, not from this ingress. So you can control that. In addition to that, what we just discussed, this particular ACL, IACL, should also filter RFC 1918, should also filter all the multicasts that you don't require, should also filter RFC 3330, which you don't require. So in addition to this that we just spoke, there are some other things that you don't need to attend to RFC 1918, multicast and all that. So deny them. Why do you want to process it? So infrastructure ACL must permit transit, and I keep emphasizing, unlike RACL, receive ACL, In RACL, we had explicit deny IP NENE at the end of the list. In the IACL, we have explicit permit NENE because we are applying IACL on an interface. We are not applying in the RP or something, we are applying on the interface. So we must make sure we allow the transit traffic via permit IP NENE. And 99.99% the best practice to apply IACL is on the ingress, okay? On the ingress of the inbound interface. So for example, if this interface facing to your service provider, you apply IACL on this interface inbound. No point of doing outbound, inbound, okay? So here is just a quick diagram. Let's say you have your core. These are all the routers and devices in your network. So let's say you have an IACL applied here, inbound. So any traffic coming from source this, destination any, should the IACL allow it? No, it should drop it. Another example, let's say any valid source, valid, not spoofed, not any bad packet, but any valid source trying to talk to any destination or any router, R3, R2, R1, should it allow IACL? No. Because why is that guy trying to send an OSPF packet to my R1? Or why is this guy trying to send a BGP packet to my R3? He doesn't need to. So you just block him at the source. You don't allow it all the way here, and then R3 receives it, R3 processes it to the RP, BGP, and says, oh, sorry, I don't talk BGP with you, and then you drop it. You will eventually end up dropping it, but the point of IACL is dropping it so earlier, on the edge. So remember that circle we said we should create a boundary, a circle outside the core. Don't wait till the traffic traverses all the way to the last box and then that last box drops it. Don't wait for the process, that BGP process to drop it. You drop it proactively on the edge. Make sense?
That's valid for management as well.
Yeah, all management and control plane, all traffic. Why are you keeping all the telnet traffic all the way here? And then you have a telnet ACL here which will eventually drop it. But you traversed all the traffic till here, unnecessarily chewing up the bandwidth. In similar way, this was negative, but this is permit. So let's say there is an eBGP packet coming in to a router CR1. Yeah, that is a valid traffic. You are peering eBGP to that box, so you permit that traffic. Make sense? So typically, again, same like RACL, it's a repetitive process. You fine-tune your IACL over the period of time. You can start with a very open IACL and then start to tighten it a little bit on a explicit source and destination. So first step is same slide deck, same process that we used in RACL. Step 1, use classification. Try to understand which protocols talk to your box. Does it talk on a physical address, logical address, real address? And then start writing the ACLs. Do not permit protocols that you can't explain. Sometimes, some guy will come and say, hey, allow this protocol just because GRE or something, IPv6 or something that you don't know whether that is communicating to the box. Again, I'm not talking about transit through the box. I'm talking to the box. So let's say your box IP address is 10.1.1.1 and there is a packet coming in IPv6 for that, oh sorry, not IPv6. There is an SNMP traffic coming in for that 10.1.1.1. Why do you care? I mean, you know that SNMP traffic is legitimate, but why is it talking to my box 10.1.1.1? You drop it, okay? So you begin the filter, you start using the classification ACL that you developed in the step 1. Then you closely monitor using show access list because you don't want unnecessary traffic to get dropped also. Okay, so you have to close using the log keywords. And finally, you use permit IP NENE. Don't forget this line, otherwise you'll be in trouble. And then step 3 and 4 is you fine tune. Fine tune as in you explicitly identify the source addresses and the destination addresses. Because in step 1, you can leave it a little open, little loose, any, or /24 to /28. But in step 3 and 4, you keep hardening it to the specific /32 host source to the /32 host destination. Okay? This is the same thing, the same process we used in RACL. The only difference is that RACL is applied on a different box and IACL is applied on any box on inbound interface facing your service provider or ingress or whatever. So here is a simple example of how you can build a IACL. Okay? You deny all the junk, you deny the RFC 1918, then you start permitting the ones you really need. Like for example, you permit eBGP from a specific host to a specific host on the port number. You didn't say any. The any can be in the first step, but this is how it should look like after a period of time, after 3 to 4 months. It should look like this, very small. And then finally, you permit all the data plane via permit IPNE. And where will you apply this access list? Inbound on the interface facing your uplink, facing your service provider.
You refer to that as an infrastructure ACL, but there is not a Cisco keyboard infrastructure.
Exactly. It's just a regular ACL, it's just a logical concept. It's a regular ACL that you apply on the links that are facing your ISPs.
The receive ACL is a specific
Is a feature. Absolutely. That's why I'm saying there are two different things doing the same thing, kind of. Okay? So if you don't have RACL, at least you use IACL. So, no, it shouldn't. It shouldn't. Definitely.
The exact same statement you got in the eBGP
Yeah.
in your control plane, but rate limited.
Yeah, you can fine tune it further. So it's like, a bit of both. So it has been successfully used over the period of years, many ISPs. Actually, this concept of IACL came up from one of our big ISPs. They used to use it as best practice, and then it started to become a concept, and we documented it, and we started educating other customers that, it's a good thing, use this. Let's call it IACL, So as you said, it's not a feature or an explicit keyword in the syntax. It's just a logical concept of how you can use traditional access list to your advantage as a security feature. Okay? That's it. Any questions? Before we go for question, I have put some very good links for the things that we talked about. So IACL, there's a good link. You can get a very good sample config. RACL, control plane policing, NFP, Network Foundation. So you can go through these links, and these slides will be available. Any questions?
Getting back to the thing that you kind of beat up on a little bit earlier about when you are deploying QoS and rate limiting, fine-tuning those numbers. Short of throwing excessive traffic at a box from a traffic generator, is there any reasonable guidelines that you can suggest?
I personally don't have any link, but I can research, and if you give me your email, maybe I can dig up something and send you this. Here, look, this is a little bit of recommendation of what the numbers should look like. But honestly, top of my head, I cannot think of any link or any document or any Cisco guide that I can give you and say, look, here is the recommended numbers that you can use.
I mean, the CCO is full of configurations.
Maybe there is something
It's
there.
got random numbers that are all different and no explanation of how they got them.
Yes. But I think I can find something to give you. So if you can get your email, I'll send you something. Okay, so if there's no further question anymore?
About the
Yes.
hardening, is there any more information on the core hardening VRF?
There is another presentation which I don't think is in NANOG, but I think you will find it on the previous NANOG slides, it's called, what was that session's name? Advanced MPLS VPN, and there was another one called, I'm missing the name. Because in the previous NANOG 41 and NANOG 40, there was a exclusive session on that core hardening and how to protect the, actually I have the slide, maybe when you finish I'll show you some of the slides.
Will you have
And
my email? I'll give you the card.
yeah,
Okay.
the Computer Science Corporation, Steve. Okay, I'll send you that.
Okay.
I'll send you the link of that presentation which talks about core hardening and MPLS VPN. Let me make notes because there will be too many things to, and I'll forget. So I have to send Steve MPLS VPN and core hardening. And your good name was?
Jay. I put a note on the back if I
Oh, J. Okay. So I have to J some sample rate limiting numbers. Okay, that's it. Okay, guys, thank you very much. I hope you enjoyed it. Thank you for coming.